Hey everybody! Today we're going to be doing the 6th video in the set theory playlist. This is going to be the final video that I have planned at least. If I have any other future videos on set theory that I want to add, I'll just add them to the playlist, and I'm not going to put them in any numerical order like they have been. So they'll just be like extra videos. Today we're going to do like a little bit of a proof, because I think we already covered most of what I wanted to cover with like elementary basic set theory, just like cardinality, infinite sets, probability functions, all that kind of stuff. I think we covered most of what I wanted to. So today we're going to do a proof. So we're going to start by letting f be a function from domain x to codomain y, and a and b are subsets of x, and they can actually be equal to x. It's kind of boring that way, but they can be if they want to. And we're going to prove that f of a union b equals f of a union f of b. So let me draw a picture to explain what that means. So if we have, let me draw the domain as a box. So if we have domain x and then codomain y, so this is also a box, and just function f here. Then a and b are subsets of x, so let me just draw a first. So this is, I'll just say this is a, and then it'll map to some, I don't know, some, let's say it maps down here. This is f of capital A, right? This is the image of f, the range. This is the image, because you can like change that a little bit if you want. But then we have it intersect with this set B, which is also a subset of x. Now, the intersection could be empty. That's also kind of uninteresting. You can play around with that if you want. And let's say it maps over here to f of b. Okay, and I'm drawing them in like different positions. You know how this is like on the left and this is down here for f of a. I'm doing that on purpose to show that it doesn't have to like look the same. You know, it can be somewhere different. So so they map, so a elements from a map to f of a, and elements from b map to f of b, and in general elements from x map to y. Okay, so what I claim is that f of a union b, which is this whole set, is equal to f of a union f of b. So this whole thing here is, so this is equal to this essentially. F of this is equal to this. So we can think of f of a, which is this, union f of b, so their union is the same as if I took a union b and I mapped that onto here. So that's what I'm saying. So the way we do this is interesting. So we're basically showing that two sets are equal, and the way we commonly do that is we show that they're subsets of each other. So if we show that f of, if we show that f of a union b is equal to, is a subset of f of a union f of b, and then we show that f of a union f of b is a subset of f of a union b, if we show that they're subsets of each other with the condition that they could be equal, then the only possibility is that they're equal, right? Because if they're subsets of each other, then they have to be equal to each other. It's like saying like, if we have x is greater than or equal to 3, but then we also have 3 is greater than or equal to x, well, if we draw that on a number line, so here, let me just put 3 in the middle. If we have x is greater than or equal to 3, so then we should say, okay, well, x is going to be all these guys. Well, it could be all of those guys. But then we're also saying that 3 is greater than or equal to x. So in other words, x is less than or equal to 3. Then it's all these guys, including that guy in the middle. So then we know that it has to be x has to equal 3 in that case. So that's kind of the same thing that's going on here. So we just have to show that they're subsets of each other. And that way it works. So let me go the forward direction first. So f of a union b is a subset of f of a union f of b. So how are we going to do this? Well, we can show that we can pick an arbitrary element from f of A union B and just say that it has to be an f of A union f of B. And if we pick an arbitrary element, then it's fine, because then we can say, okay, well, we can pick any element from this set and it'll be also in this set. So that's kind of the argument that we're going to make. So we're going to say, typically we say let x be in f of A union B, but since f of A union B is in the codomain, I'm just going to say pick a y. So let y be in f of A union B. Okay, so this is a pretty basic statement. We're just taking some element from f of A union B. But what that means is that there exists some element x which is in A union B, such that f of x equals y. Okay, so what I'm saying is that, well, we have to have some element here in A union B. Let's say it's like over here, or it could be over here, it doesn't matter, as long as it's somewhere in that shaded area. So f of x equals y, so that's where f of A union B goes to. So f of x equals y. Makes sense, right? So there exists some x in there such that f of x equals y. So we can start by saying, well, if I'm not going to write this as complete sentences, but if x is an A, that implies that f of x is an element of f of capital A, right? Because then, like, f of A is the image of A under f, the image of A under f, and so then f of x would be in that if x originated from A, but if x originated from B, then f of x is in f of B, right? So x can be in A or B, it doesn't really matter, but in the end, if we're saying, well, if x is in A, then f of x is in f of A, and then if x is in, or if x is in B, then f of x is in f of B, then basically it's like f of x is in f of A, or f of x is in f of B. So if f of x is in this or this, then f of x has to be in f of A, or, which is union, f of B. And so that's the forward direction proven, okay? Now we just have to go backwards. So let me erase the board real quick, and then we'll go in the backward direction. Okay, so to go the backward direction, we're going to start by saying, basically we want to show that f of A union f of B is a subset of f of A union B. Or in other words, the reason why I drew it backwards is because it's like f of A union B is a superset of this guy. So basically we're going to start by saying let y be an element of f of A union f of B, and we're trying to show that y is also an element of this guy, right? So this directly tells us that y is in f of A or f of B. So if y is in f of A, then x is in A such that, and I'm going to put st for such that, f of x equals y. Or if y is in f of B, then x is in B such that f of x is equal to y. So again, the same thing. So like I said, y can be an element of f of A or f of B because it's the union. So if y is in f of A, then that means that x is in A if we have f of x equal to y, or x is in B, or if y is in the f of B, then x is in B. So what this tells us is that x is in A or B, right? So x is in A or B, which is union. So then f of x, so I'll say that implies that f of x is in f of A or B, A union B. And that's it. So we started with this, f of A union f of B, and I showed that f of x has to be in f of A union f of B. And again, f of x is just y, so it doesn't, the notation doesn't really matter. And so we proved it both ways. And so that means at the end, since we showed that we showed this direction and then this direction, we showed both of those, then that means we showed that they're equal to each other. And so yeah, so f of A union B is equal to f of A union f of B. Now this isn't a formal proof because I didn't write it in actual English. I just kind of wrote, you know, a bunch of symbols and stuff. But yeah, if you want to formally prove it, like if you want to write it out, you would have to, you know, do it. You'd have to write complete sentences, not no STs, or you can have implication symbols and stuff, but just use them only when necessary. So yeah, I hope you enjoyed this little proof. Thank you guys so much for watching, and I'll see you in the next video. Bye guys.